Welcome to Calculus 3, day 10, I think, part 1. We're talking about partial derivatives. So we need to find a way to look at the derivatives of these 3D functions, right? And the partial derivative in respect to x and partial derivative in respect to y, will reveal derivatives only in the direction of x-axis or the direction of the y-axis. So if we take a look at the graphic provided in a textbook, which is a pretty nice one, we see a saddle point. And then next to it we see the hills and a man walking in between. And we see roads. Now, since this saddle point has the 0, 0, 0 right here at the saddle point, that's where the man actually is. There's the x and y axis going through that point, and we are able to find the derivatives in those directions. Now, as you can see, the north points this way and the east points that way, which means that's west, right? The south goes in the back. So these derivatives would be east-north and east-west and north-south. The derivatives give us, so the partial derivatives will only give us these two directions. Later on, we're going to learn something called the directional derivative, which can find the derivative in any direction. For right now, partial derivatives will only give us derivatives in respect to x-axis and respect to y-axis. Now, with derivatives, we know we're still getting velocities, accelerations, and all that kind of stuff. It's just we're learning the mechanic of the partial derivative, and we are supposed to understand that these derivatives are strictly in the direction of x-axis and the direction of y-axis. So, and the derivative is what? Is a change. So that's what we are measuring. For any shape that you might have, right? Any shape that you might have, you're going to pick a point somewhere on that shape, and you will put the little, in your mind, little x and y coordinate system through the point, and when you take the derivative in respect to x, the slope could go up, could go down, and then you will know you would be able to understand that point and the neighborhood of that point. So the proof for this is going to be identical to the proof in Calculus 1, which means that we have the limit definition of the derivative. Partial derivatives have their notation as fx or partial f divided by partial x. So these are all different notations for it. So we have fx of xy. We can also say partial derivative of f in respect to partial derivative of x. It's going to be the limit of h goes to 0, if you remember your Calculus 1 at all. And then what you have? You have x plus h minus f of x divided by h. Now, what's happening with y? Well, I forgot about y, so I have to add the y. There's a y there, minus f of xy. But you see that this y will not impact at all because there is no change in y. Fy, same. So these are the definitions that we have for derivative, called the limit definition of the derivative, multivariable and all that. We find tangent lines again and again and again. So that doesn't change. We have all of that stuff. Well, we're going to omit looking for the derivatives long way. We can immediately talk about taking partial derivatives immediately. So what do I have? Problem 14. F of xy is equal to y to the 8 plus 2x to the 6 plus 2xy Let's find partial derivative in respect to x. Well, if we are taking a derivative in respect to x, y is held as constant because, remember, we are looking the x-axis, so y has to be constant there. So what is the derivative of y? 0. Plus the derivative of 2x to the 6 is? Very good. And then plus 2y. Y is held constant, and we just get to copy that. Derivative of x is 1. What's the partial derivative in respect to y? Eight y to the 7 plus 0 plus 2x. Very good. Now, obviously, we don't write this plus 0. It's just we are practicing for the first time. So problem 26. H of uv is equal to the square root of uv divided by u minus v. There we go. Good luck. What's the partial derivative of h in respect to u? Put those derivative skills to use now. Yes? So far, 100%. I know, it get worse, right? Here. So yeah, it's this over here. Like these four. I'm not definitely. Did you ever play Civilization? What happens? Civilization. I'm FPS guy, yeah. Well, I do play Diablo. All right, guys. Let's take a look. So, we have the partial derivative in respect to u. So u is the variable, and v will be a whole constant. So we have 1/2 uv over u minus v to the negative 1/2. So this is the derivative of the square root. And then we have the chain rule. which is the derivative of the inside, which is quotient rule. Very good. So for the quotient rule, I actually don't need the parenthesis. U minus v squared in the denominator, u minus v in the numerator times the derivative, so that's just v, minus uv times 1. Perfect. Now, we can try and simplify this a little bit. So partial derivative of h in respect to u is 1/2. Now you see the negative sign. Negative sign in exponent flips the fraction. So I can write this as u minus v over uv. That takes care of the negative, and the 1/2 is the fact that I have a square root there. And then what do I have here? I have uv minus v squared minus uv divided by u minus v squared, and then these two cancel. So u minus v and then uv times negative v over u minus v squared. We could technically, negative v squared, that's what I said, please pay attention. Very good. So that's what we have. And that would be the partial derivative. So we had to use the chain rule, and then there was a quotient rule embedded. As long as you are grasping the fact that one of your variables is a variable, the other one will be held a constant, or other ones, because you can have multiple, you will be good to go. Be wary of the chain rule, product rule, quotient rule, right? All of that stuff. Let's do one for more than two variables. All of these partial derivatives, I believe, are straightforward as long as you know how to take the derivative. So how about let's get something cheaper, and then we'll get spicy. So h of xyz is equal to cosine of x plus y plus z. Find all three partial derivatives. Find hx, which is partial h partial x. Find hy, which is partial h partial y. And find hz, which is partial h partial z. So find all three partial derivatives. Yeah, it's a little bit troll question. So this is exactly what. You want it? And then you can start. It's Gatorade. It's Gatorade. So what is the answer? For all three of them is the same. Sine of x plus y plus z. Very good. That's what I said. So the chain rule should be applied to the argument of the cosine. So derivative of the cosine is negative sine, and that goes for all three. And you have to copy the argument, and then times the derivative of the argument. Now, for the first one, derivative of x is 1. And the second one, derivative of y is 1. The others are 0. And the third one, derivative of z is 1. So that's what we get to multiply. Times 1, times 1, times 1. Now, those ones are all 1, so they're all equivalent, except we obtain them from different x or y or z variable, depending on which partial derivatives we were taking. So the answers did come up to be the same. And this is one nicely symmetric function in that respect. Let's take a look at this. Oops. The square root. So let's find all four partial derivatives. It's backwards D. Backwards 6. All right. You had plenty of time to try it. Let's see. So first, in respect to W, what would be the answer? Just the square root. Very good. So if you are looking at this, guys, if W is your variable, that means that all other variables are constants. So when you do the combination of any kind of those constants, the whole thing is a constant. So derivative of W is 1 times the constant, so just get the constant as the answer. Good. Now we are going and taking derivative of the rest. We have partial derivative in respect to x. So what do? Well, we have w over 2, right? Because w is a constant, we have to copy that. And we have to do the chain rule, very good. So it's w over 2. We have x plus 2y plus 3z to the negative 1/2 times the derivative of the inside, which in this case is just 1, because the derivative of x is 1. That's the chain rule. So the answer over here is w over 2 square roots of x plus 2y plus 3z. So not 0. The derivative of 1/2, the square root is a 1/2, the exponent drops down, so it's 1/2. So now we have for 2y, we have the same story, w over 2, x plus 2y plus 3z to the negative 1/2, and now the derivative of 2y is 2, which will cancel the other 2, so we just have w over the square root. And then finally, w over 2, x plus 2y plus 3z to the negative 1/2 times 3, which is 3w over 2 times the square root. And yes, you are guessing well. Eventually you're going to set this equal to 0, look for critical points, and find min and max by the end of the chapter. I know, awesome, right? So you want to have these as factored as possible. And actually, if you get a question like this, you're very lucky, because this is extremely easy to solve, any one of these, because all of the busy stuff ended up to be in the denominator, so when you set equal to 0, it just dies. You just have w equals 0 for each one of these, so easy, cool, right? It's this. And we'll see some scary examples when we get there eventually. So that's the partial derivatives. So when you learn the derivatives, you learned about the limit definition for the derivative, then you took a whole bunch of derivatives with product rule, quotient rule, chain rule, and then, but we can have a second derivative, right? And the third derivative, and the fourth derivative, which means that we can have the second partial derivative, second or third partial derivative, or so on. And then, even better, over here, we can have mixed partial derivatives. So you can find that, right? It's going to be annoying as hell, but you can do it, right, if you're careful enough. Oh, I forgot W. There we go. Depends on what the application calls for, which is when you start, your physics and high-end engineering courses, this stuff is going to pop up. So let's take a look at, second partial derivative, third partial derivative, and so on. Let's start with a vanilla problem. Yes, sir. No, that's it. These are the regular functions. Except when you have 4 variables, you have 3 variables of time, of space. The fourth one could be time. The fourth one could be temperature. The fourth one could be something that it's added to the mixture, right? So. What happened?
If you have like a function that's dependent on x, y, z,
okay.
You only plug in x and y.
Well, it depends if it's implicit or the explicit form, because that could be the 3D or a 4D, depending on how it's written. Yeah. It's coming up. It's coming up. Problem 30. 2x to the 5y squared plus x squared y. And let's find fx, fxx, fy, fyy, fxy, and fyx. Xx is the second derivative. Very good. So you find the first derivative and then you find the second derivative off of the first one. No primes. No primes. Either the squiggly piece or the lower. Still recommending. You should.
So the y, so what you find x is the y behind.
Try to do it before. Don't do it. Yes. Definitely one or two of you will. There you go. So it's Rockwell or what do you? Sure. Of course. Let's go. What do you mean? There, we are taking the picture.
So this is certain.
Oh, okay.
No, so remember yesterday when we had contour maps? That's what.
You take the derivative y. So when you for this derivative, you take from here in respect to y. It's like a chain, right? So this is you take the derivative. So first derivative is x derivative, which is this line, and you take another derivative here. This is the y from there, and then the second y going off of this one. That's the second derivative. These are the second derivative, but they go off of this one, and that one x off of that one. And they call it mixed derivatives.
Is it just like
So
x, y? We just
see this? They're the same. So you will be taking the derivative in respect to y off of this one.
Oh, and with respect to y.
In respect to y.
So x being not right. We can just do. I'm saying there's fxy. So it's x and y squared. Actually, that's just product.
Yeah, that's what I did. Oh, wait, explain that again?
I will.
And he said that it's
This derivative, and you take the derivative in respect to y over that.
so you take whatever you got for y.
You take in respect to y. Yes.
Second derivative.
Yes.
So that means that I don't today getting
Oh yeah, this, that would be yeah, this.
only those school.
We just, I just find it easy and then I just go, I'm just gonna do it. Because I wanna do it. Yeah, it's just, I have to do the work.
All right, guys, let's take a look. Please pay attention because this has new concepts here. So we will start with taking the partial derivative in respect to x. That's the first line. So x is a variable. We have 10x to the fourth y squared, because y squared is a constant, we just copy that, plus 2x y. Y is a constant, we copy. So we are done with the first derivative. The next line means take derivative again in respect to x. So 40 x cubed y squared plus 2y. Now we are supposed to find the partial derivative in respect to y, Mary. So we have 4 because the y squared, right? That's 2y. So 2 times 2 is 4. X to the 5 y plus x squared only, because the derivative of y at the end is just 1, so it's x squared. For the next line, the fourth one, we are taking another derivative in respect to y off of the previous step. So it's going to be 4x to the 5. And then derivative of x squared is 0 because it's a constant, right? We're taking derivative in respect to y. Now the next two are known as mixed derivatives, mixed partial derivatives. You see that the first derivative is to be taken in respect to x. Well, I have that done already. And then the second derivative needs to be taken in respect to y off of that f of x up there. So now I am taking the derivative in respect to y, which is going to be 20x to the fourth y plus 2x. Because I was taking the derivative in respect to y. Now we're going to go to the second one. Do this partial derivative here off of the partial of y. So please note this over here is partial of y. And then you need to take the derivative in respect to x off of the partial y you already did. So we're looking at the partial y and taking derivative in respect to x, which gives us 20x to the 4 y plus the derivative of 2x in respect to x is 2x. Yes.
Why, how come it's not 4x to the x plus?
This one? We're talking about this one?
No, 2x.
we are taking the derivative of this with respect to y.
Right.
So this is the variable, this constant. I copy the constant. The derivative of y is 1. So times 1 plus the derivative of constant is 0. Because I'm taking with respect to y. X is constant.
Right.
Yes, ma'am?
Is this a special case where those last two derivatives are
No,
the same or
it's a
no?
theorem that we are going to cover soon, which says that the mixed partial derivatives do not depend on which order you do them in, which means they're always going to be the same, regardless of the order that you take. As long as you have enough of those derivatives, so it could be x, y, x, it could be x, x, y, it could be y, x, x, in every order you do them, except as long as you have two x derivatives and let's say one y. That has to be preserved, yes. Yes, but total derivative is when you add all of these guys together. Okay. So now we are going to talk about, we saw the first partial derivative, which is the fx, fy. We saw the second partial derivative, which is fxx, fyy. And then we saw mixed partial derivatives, which is fxy and fyx. You just need to be careful in which order they are presented so that you can go to the correct derivative and then keep doing the derivative from that point on. So theorem 12.4, equality of mixed partial derivatives, says assume that f is defined in an open set D of R2, then f of xy and fyx are continuous throughout, and they're the same. So mixed partial derivatives are the same. It doesn't matter whether you find fxy or fyx, and obviously you will opt for the easier calculation, right? That all depends also on your experience, because one way you might have to deal with product rule, the other way might just be vanilla derivatives, depending on which way you approach the situation. And obviously doing 5,000 problems makes everything better. And your applications, again, you take any formula from physics that has a lot of different variables in there, or chemistry, and just take a whole bunch of derivatives and see how change impacts everything. So they did over here the ideal gas law, the famous equation that for whatever reason, it's very interesting. You go through all of physics, you might not remember any of it, but for some reason this formula always sticks, and it's so random. I don't know why, but the famous PV equals the nRT formula for ideal gas law, and the book actually has both N and R mushed together into one constant, so PV is equal to KT. This is the relationship between the pressure and the volume and the temperature. So what do you know? Well, maybe you're not paying attention to it. You should. That through the winter, through the summer, the pressure in your tires should not be set to the same level. When it should be lower? Winter or summer? Summer, lower pressure. Why? Yes, it's hot outside, plus driving creates friction, which means additional heat, which means larger temperature, right? So with larger temperature, you have larger pressure. All right, let's solve for pressure. So pressure is equal to KT over V. So all of these, P, T, and V, they're all variables. And when we start taking partial derivatives, we can track the change in any one of these. So it says, find the partial derivative of pressure in respect to volume. Now, can anyone tell me physically, what does this mean, this question? Partial derivative of pressure in respect to volume. What are we trying to learn?
As volume changes, how does it affect pressure?
Okay. Say it, Tim. There's no temperature there. Why are you mentioning temperature? You have it backwards. Okay, so in the end, guys, what this is it's measuring the change of pressure in respect to change of volume. Some of you said this, so yep, I'm repeating it. So change of pressure in respect to change of volume. So we take the derivative, observe that KT are constant, so we copy KT. And what's the derivative of 1 over V? Negative 1 over V squared. Very good. Now, can anyone analyze this equation and tell me what's happening here? What's physically happening with the whole thing? This will be a cool question for exam to see if you understand the derivatives and stuff in application. Write a paragraph, 3 sentences about this. Technically, your project, write 10 pages about 3 problems I give you, but this is more of a... So the change in pressure in respect to volume is going to be... Yeah, but what is the negative doing there? Decreasing. Aha. So K is a constant, we don't touch that. So we see that negative t, right? That should decrease. And it's inversely proportional to the square of the volume. Inversely proportional to the square of volume. So that means that the change in pressure will decrease with temperature and inversely proportional to the change to the volume squared. Think about it.
Why do we derive the volume?
We can find any one of them. V is the variable. V is the main variable now. If you're looking in respect to V, right? It's a partial derivative in respect to V. So V is the boss. V is the variable for the problem. The others are constants all. Not time, temperature. We can do any of these, guys. Let's find change of pressure in respect to temperature. What is that? K over V. Derivative of T is 1. The rest are constants. So the change in pressure or the change in temperature, yeah, is only inversely proportional to the volume. The change in, well, not the change in volume, the volume. Does anyone remember related rates from good old days? You see how you have K over V over here? So technically, we're not going to be doing this, unfortunately, but you can combine this and get the related rates problem going. So change in pressure with a change in volume is going to be, so negative T over V has to remain times change in pressure over change in time, temperature. And there's your related rates related to this equation. So if you know how one changes in respect to the other, in which case some of these you can measure, you can compute certain things. We are not going to be messing with this, unfortunately, in a class. Well, you know, eventually you might take a modeling class for your engineering courses, and then all this stuff is going to pop up. And then you will remember me and what I said about these things. All right. Do we have anything else? Technically, that's it on partial derivatives. So we're going to stop the stream and then hit the break when we come back. Next section, 12.5, chain rules. And I had that S at the end, chain rules.